Okay. Okay, so we're down to let's learn about singularity. So the non-analyticity of the cosmological correlators tell us about the physics of what's going on. Okay, so for now, I'm going to discuss flat space, massless field. But now let's go beyond the Gaussian approximation. Okay, I'm going to compute the 3-point function. 1, 2, 3 for a phi cube theory. So there's the Lagrangian contains some phi cubed. Now, well, what are we supposed to do? We're supposed to evaluate the action at a classical solution that asymptotes to wave number right. So we're gonna get in the wave function. We're gonna get some coefficient psi3 that multiplies phi of k1, phi of k2, phi of k3. Okay. And what are we supposed to do? We just need to do time integral. We evaluate the action. So the quadratic part of the action is just going to give us a Gaussian wave function. But now the cubic part is what's going to give us the non-Gaussian correction. So psi3 should go, and I'm not going to keep track of factors of pi and even I. I made the points that these are complex saddles, and we're going to compute the wave function. And now I'm more worried about learning the rules of the game, what the singularities are. And we're doing it in flat space. We'll get to the sitter later. Okay, so I need to do a time integral. Okay? So there's some time, and here's eta star. And well, there's G phi classical cube. But if I'm interested in selecting the wave function coefficients that goes like phi of k1, phi of k2, phi of k3, then if you Fourier transform, there is only a time integral to do. Integral over time. These are the late time profiles, and we just check in the, if you wish, the bulk to boundary propagator, okay, of momentum k1, eta, bulk to boundary propagator k2 eta, bulk to boundary propagator k3 eta, where the bulk to boundary propagator is e to the I k let me put eta star for now, I k eta minus eta star. Okay, I was in the previous lecture I was imposing that there is some specific profile phi k for each wave number. Now I'm just pulling it up front and normalizing, so there's unit norm for each wave number. Okay, so that's it there, and then I integrate from minus infinity with the appropriate I epsilon prescription to kill the oscillations at early times all the way to eta star that I'm going to take to 0 eventually. But well, this is, so you're like, oh, what's the big deal? That we can do. Well, it's e to the I k1 plus k2 plus k3 eta minus eta star, which if you were doing scattering amplitude in flat space, you could have also computed the on shell action. There's a G, sorry, there's a coupling constant here. And then you would have integrated from minus to plus infinity. And what's the result of the integral in that case? Delta function. What is this known as? Energy conservation, okay? K is just the energy, omega 1 plus omega 2 plus omega 3. So if you did the integration over all of flat space, you would have got an energy conserving delta function. Here, because you integrate up to some finite time, you broke time translation invariance. You're not conserving energy, but you get, the boundary term dies off, and here you get just GIG divided by. Okay? So instead of getting energy conserving delta function, you get a pole. So contact interactions, that's a general lesson. Contact interactions. The only admissible singularity is going to be total energy singularity. Okay? 1, 2, and the numerator can be some function of the momenta. For example, beyond 3 points, you could have imagined derivative interactions. So the derivatives would produce factors of k upstairs, okay? K1 dot K2 and so on. But the important thing is that the only admissible singularity coming from this time integral that would have given you energy momentum conserving delta function gives you this total energy, this pole. So this is called the total energy singularity. So contact interactions only have, let me call this K total, okay? Maybe some notation. Let me call this K1, 2, 3. Okay, just the sum of K1 plus K2 plus K3 or K total. Only have K total singularities. Okay? So you can bootstrap all of them. You just write whatever you want with K total singularity, and the numerator is almost free, almost completely free. There is a catch though about the possible numerators. Let's look in this example here. When I send K1 plus K2 plus K3 plus 0, which in the physical region I cannot because it's just a sum of positive numbers. But remember that K is a square root of K squared. So in terms of analytic function, there is a cut. You can make the square root pick up a negative sign. And outside of the physical region, you can send this to 0. So you will blow up, and the residue at the pole is the scattering amplitude. And this is a general result, okay? So the limit as K total goes to 0 of the wave function, well, the flat wave function, is 1 over K total times the scattering amplitude for the same process. Okay. In flat space, it turns out that things are always simple poles. That's the reason why we focus on flat space first. In the Sitter space, you can have powers of K total. Okay, but more or less the same story goes. Contact interactions can only have singularities in this kinematics when the K total goes to 0. And the surprising thing is that in the Sitter space, when you send this K total to 0, the de Sitter wave function becomes singular, and the singularity is again the flat space scattering amplitude. So the flat space S matrix is contained in an interesting way inside of the wave function of the universe. But why is that? Well, the reason is, you can see just from this simple example, when you send k total to 0, so the integral is peaked around horizon crossing, right? When k eta is order 1. So when you send k total to 0, the integral is becoming peaked at earlier and earlier times. So it's peaked at such early times that the perturbations, again, don't know about the existence of a boundary. So they just interact as if they are in flat space. In de Sitter, they get so blue shifted that they again don't know about the de Sitter horizon. Okay, we're going to see that the answers become the de Sitter invariant answers in these limits become Lorentz invariant. So that's a nice sanity check of the result. So this is kind of a fundamental result to make sure that you're doing reasonable things. You should go and send k total to 0 and check that the wave function diverges, and the coefficient of the divergence is the analogous process in flat space for the scattering amplitude instead of the wave function. Okay. Well, at 4 points, nothing changes for contact interactions. So let's try to do something a little bit more complicated. Let's do an exchange diagram. Still in flat space, okay? Okay. So now there's K1, K2, K3, K4, and let's see what notation I used here in my notes so that I'm This is S channel, okay, so I call it KS. KS vector is K1 vector plus K2 vector. And as usual, if I remove the arrow, it means I'm taking the absolute value. Now, there is a novelty because there is a propagator from a bulk time to another bulk time. So what am I supposed to do? This is phi cube theory. I'm supposed to evaluate the... I'm just trying to follow some Feynman diagram type of prescription, okay? Now, I need to evaluate the on-shell action, and long story short, I'm just supposed to multiply propagators like you would in flat space, okay? So let's stare at the diagram and see what propagators we should multiply. So there, let me call this eta 1, eta 2, then there's eta star here. And I'll set it to 0 now because it's not relevant what eta star is. So there's going to be now integral. There are 2 time integrals to do over eta 1 and eta 2. There's going to be bulk to boundary propagator for particle 1, eta 1, for particle 2, eta 1, then times some propagator that we call bulk to bulk propagator, Ks eta 1, eta 2, bulk to boundary propagator, K3 eta 2, bulk to boundary propagator, K4 eta 2. Is that clear? I'm just taking, let's stare, the formula should make sense given the picture, okay? So in time 1, eta 1, I have a propagator momentum K1, propagator momentum K2, okay? And I have the propagator from time 1 to time 2 with momentum Ks. Okay. Now, here I have propagator momentum K3 from time eta 2, propagator momentum K4. Okay? So what is the novelty is this guy here. So as usual, when you propagate in space-time, you need to take a Green's function. This was solving the classical equation of motion because you wanted to fix some boundary condition here. But now I really want the propagator for the wave function, but it needs to implement my boundary conditions. What were my boundary conditions? I wanted to select the vacuum in the past, so they better behave as like e to the ik eta when I send each of the two etas to minus infinity. But now I already fixed the boundary condition with these bulk to boundary propagators. I don't want these guys to mess up the field profile when I send eta 1 or eta 2 to eta star equals 0. So what do you suggest I do? What is the second? So one boundary condition, let's keep eta 2 fixed, okay? One boundary condition is that as eta 1 goes to minus infinity, should behave like plane wave. It should go like e to the I ks eta 1. That selects the vacuum. Now, what am I supposed to do when eta 1 goes to 0? No, I already fixed the boundary value. So it's not supposed to... I use these guys here to fix the boundary value. Remember, this sets up a wave with unit norm. So I don't want this guy to put anything at the boundary. So what am I supposed to impose? 0. Should be 0. So it's going to be different than the usual. This guy here selects a special surface, okay? There's a special time in which I do my measurement, and this propagator better, it's kind of Dirichlet boundary condition, so I hold fix the value of the field here. These guys are already fixing the field profile I want, so it better be that this guy, if I drag this eta 1 to the boundary, that this propagator vanishes, okay? And you'll see that it's a tiny modification to the propagator that you're used to. No, because they're doing different things, right? This guy is setting up, he has unit norm here, right? Well, this guy here, I'm telling you that it should vanish. So they're just two different types of propagators. One sets up the field value I want, and the other is just a Green's function that connects two different bulk points. But it's... Why? No, I think it's the same. It should also vanish when you send the z to z. No, I think it's the same boundary condition for the ADS CFT bulk to bulk propagator. Yeah. No, it's if you do Euclidean ADS CFT, this is the usual bulk to bulk propagator. So here's what the propagator is. These guys here are the ones that are setting up the boundary condition. So you don't want this guy to come and mess up with these. There is some story of the surface at which the propagator is supposed to vanish. And if you take a derivative of this propagator with respect to the position of the surface, you can break it apart into products of bulk to boundary propagators. But that has nothing to do with the boundary conditions that it satisfies. So there's some connection of these two bulk to boundary propagators, but you need to hit it with a derivative. So maybe that's what's causing the confusion. So this guy here is, here I need to make sure I don't mess up. Given by this formula. Let me copy this so I don't give you the wrong answer. This is the usual Feynman propagator, okay, time ordered propagator. So for example, notice that if eta 1 is much earlier than eta 2, if I'm sending this to minus infinity, it goes like a plane wave, e to the ik eta 1, okay? But now I want to impose that it vanishes here, so I subtract off this term here. Notice that it breaks time translation symmetry, okay? Because I picked specific surface. Okay? So it breaks time translation symmetry. So that's the novelty, this term here. This is the usual Feynman propagator. Now we can do this integral. I mean, as you can imagine, it's simple to do. It's a bunch of exponentials, right? This thing is e to the I k12 eta 1. This is e to the I k34 eta 2. And then you can just do the integral. There's nothing mysterious. And but the answer looks kind of neat. This is so this psi 4 is given by this formula. First of all, despite the appearance of this Ks here in the propagator, the residue cancels when you add. So there are three terms: one time ordering, the second time ordering, and the guy that imposes the boundary condition. When you put everything together, you get something that ties up things in a neat way. So let me write it like this: K1 plus K. This is a cute formula. So now there are three singularities, not just one. Okay? What are the three singularities? So this is the total energy singularity, right? Just like the contacts interaction. So this is not new. This is still there. But now there are these two separate singularities. You see, what is this? It's the sum of the energies that flows into this vertex here. K1 plus K2 plus Ks. And analogously, the other one, K3 plus K4 plus Ks, is the sum of the energies that flows into this vertex. So now these are partial energy. Singularities. So in flat space, what are the possible singularities of a 2-to-2 scattering amplitude in flat space at 3 level? How many different places in kinematic space? How many different locations? Let's say it's a massless theory, okay? There are no massive resonances. For a massless theory, what is the 3-level structure of a scattering amplitude, 2-to-2? You're gonna learn this in 2 weeks, but maybe I spoil it for you now. What do you think? 1. Where else? That's it. 2. That's it. Yes. Thank you. ST and U. That's it. You can only have simple poles in ST and U. Okay? That's it. These are the only locations. And they have to be simple poles. That's why you will learn in 2 weeks that massless higher spin theories don't make sense, because they will inevitably give you double poles. Gravity is the last massless theory in which you can have all poles together, because the amplitude is STU. It's simple pole in all ST and U channels at the same time. Okay. And if you try to do higher spin theory, you inevitably have a square somewhere here, or cube and so on. There's no way around. So it's not a local theory. So here, this is S channel, and the S channel has 3 singularities. Has a singularity in total energy and has 2 partial energy singularities. This is because we cannot boost to the center of mass frame to just say that there's an S channel singularity. So S channel is now partial energy to the left and partial energy to the right. So 3-level wave function of the universe at 4 points will have 7 singularities. 2 in the S channel, 2 in the T channel, 2 in the U channel, plus the total energy. Okay? So it's an object with a more complicated analytic structure. But let's see what happens when you zoom into the singularities. Remember that the intuition is that when you zoom into the singularities, you're sending part of the diagram or the whole diagram to very early time, so that you forget about the boundary here. So if you take the total energy to 0, you're just dragging the whole diagram to the past. So so psi 4 as E total goes to 0 becomes 1 over K1 plus K2 plus K3 plus K4. K3 plus K4 is minus K1 minus K2 in these limits, and then this becomes minus K1 plus K2 squared plus Ks squared G squared. What is this? Do you recognize this? No. It's a massless theory. Remember that these are 3 momenta. Does this object, you see there's a relative sign. What is Ks? Ks vector is K1 vector plus K2 vector. So Ks is the absolute value of the sum of the 3 momenta. Well, this is the sum of the energies. So what does this look like? It's Mandelstam mass. It's P1 mu plus P2 mu squared, which is S flat. As you should. It's the flat space scattering amplitude, G squared over S. Okay? Now, when you send the partial energy to 0, then there's something amusing that happens. K1, you get a bit of a centaur, a hybrid of 2 different objects, because you're keeping this vertex fixed and dragging this one to the past. So this guy here, you get scattering amplitude, while this guy here, you get wave function. But because you're forcing this vertex to come from the past, there's something a little bit funny that happens. We can tell many stories about the meaning of this, but I'll just tell you the result. So the result is you get 1 over K1 plus K2 plus Ks. Now, this becomes minus Ks, okay? And this becomes G times some object that we call the shifted wave function. What is the shifted wave function? So you take the momentum that you drag to the past, it's Ks, put here. Then you compute the 3-point wave function. So you see this is a 3-point wave function. K3, K4. But now you flip the sign. Ks minus psi 3, K3, K4, Ks. So you get a hybrid of flat space amplitude. So the g squared, you should think of it as g times 1, which is the flat space scattering amplitude of 3 massless scalars, times a g times, there's a g here, g times the, well, it's inside of psi 3, sorry, times the 3-point wave function. So that's to say that in these partial energy singularities, you can reconstruct the answer from lower points data. It's a bit like factorization. If you remember, or if you don't, you will learn in 2 weeks again, that if you sit on the pole of a resonance at 3 level, the amplitude factorizes into lower point amplitudes, okay? This is the analog for the wave function. So there is no sense in which you can sit on the S-channel pole, but what you can do is you can drag these 2 points to be very far away, in which case you get a 3-point amplitude on the left and a 3-point wave function on the right. And that's what you see here. I showed you this in the simplest example of flat space at 4 points. This is true in the Sitter space at any number of points. So all the singularities of a cosmological correlator are related to taking sums of energies that flow into a vertex or collection of vertices to 0. When you send this sum of energies to 0, the thing breaks apart into pieces. Okay? We can even predict. Let's predict. One, 2, 3, 4, 5. K1, K2, K3, K4, K5. Let me call this Y12. This I'll call Y23. Maybe bad. Y123, Y345. Sorry. What are the singularities of this correlator? Maybe we can't compute it, but can you predict where the singularities are? So, tell me. 1. K1 plus K2 plus Y123 goes to 0. Good. What else? Good. Well, this last one I'll just copy. What else? Total energy. What else? So what is the physics? So this guy, I drag this one to the past and keep the rest. So it's like 3-point scattering amplitude times shifted 4-point function. This guy here, I get 3-point scattering amplitude times 3-point wave function times 3-point wave function. This one likewise. Total energy, I get 1 over Mandelstam. Okay? Are we done? How do I drag these two to the past? What am I supposed to send to 0. No, the energy is flowing in. Look at the box, what's flowing in. Last one, K3 plus K4 plus K5 plus Y, 1, 2, 3. So if I drag this, I get 1 over S for this 4-point scattering amplitude times this 3-point wave function coefficient. So now you can go home after your bistecca fiorentina tonight and you can check all the singularities of the flat space wave function. Now there's one more spectacular thing about this model, which is you can find the answer just by drawing a picture. Okay, so let me tell you. You can, if you want to see the proof, you can look at a paper of Benincasa, Postnikov, and Arkani Hamed called Cosmological Polytopes and the wave function of the universe. But look here, we just had S channel, so let's draw kinematic space, okay? There's K1, K2, K3, K4. And it's just S channel, so I only draw this diagonal here, okay? If I had S and T channel, I would have the other diagonal. But I'm just drawing this S channel diagram here. Now, what does this look like to you? If I stare at the figure here. So this is the total perimeter, okay, of the... K1 plus K2 plus K3 plus K4. What is this term? K1 plus K2 plus Ks. And this term, K3 plus K4 plus Ks. So there's a prescription. You take the polygon in kinematic space. You draw the diagonals that appear in the diagram. Then you draw all the triangulations, subpolygonations. You multiply all the perimeters, and you're done. That's the answer. Some operation that doesn't touch at time integrals at all, that gives you the right answer. So I will write the answer. Let's write it for that 5-point function over there. And tonight, if you're not feeling very sleepy, then you can check all the singularities, see factorization, fall in love with the subject. Okay? So let's see. K1, K2, K3, K4, K5, Y, 1, 2, 3, Y, 3, 4, 5. Now there's a novelty in this case in which there are two polygonations, okay? First, you always break into sub-polygons. So the first thing I can do is I can do this. Let's see if I have enough colors to make this understandable. So this is one, I break into smaller tiles, one piece at a time, okay? So I cut here the big polygon, I broke into these two tiles. Now this guy I can break again, and I get these two guys here, okay? Let's see, what is the answer? 1 over, okay, 1, 2, 3, 4, 5, the whole perimeter, times K1, 2 plus Y, 1, 2, 3, times, all the K3 plus Y, 1, 2, 3 plus Y, 3, 4, 5, times K4 plus K5 plus Y, 3, 4, 5. So this is the blue guy. This is one of the yellow guys. These are the two red fellas. And then there is this polygon, which is y1, 2, 3 plus k3 plus k4 plus k5. But now there's another. You can also look at the other polygonation. Okay, so again, you start from the big. You start from the big polygon. Then instead of breaking into two tiles like this, you can break it into two tiles like so. Like this, okay? And then there's going to be an extra term. So the final answer, when you have to add them up. So the final answer is going to be, so the only thing that differs is this bigger tile that encompasses two triangles. So there's a common factor, which is k1, 2, 3, 4, 5, times the perimeter of the little triangles, k1, 2 plus y1, 2, 3, k3 plus y1, 2, 3 plus y3, 4, 5, k 3, 4, okay, 4, 5 plus y3, 4, 5. Times, now the only things that that differ are the two k from the top guy is just k3, 4, 5 plus y 1, 2, 3 plus 1 over k 1, 2, 3 plus y 3, 4, 5. This is the answer. You can do it. Huh? I add them together because there are two ways of breaking it into smaller polygons. Well, I'm supposed to break it until I have the smallest possible polygons. So there's three triangles, right? So there's just two ways of descending from a big thing into three blocks. It's just that's just the rule. I made up some crazy rule. You break the polygon into sub-polygons one at a time, okay? And I can, the first cut, I cut either here or here. If I cut here first, then the second cut, I cut here. Or I cut this one first and this one first. And the order matters because I end up with either this guy here on the first step or this guy here. And then I add them up. And lo and behold, this crazy set of rules gives you the answer if you do the honest computation. You can stick in the propagators. There are 9 terms, right? There are 9 terms. There's each propagator has 3 terms, the Feynman stuff plus the boundary condition. There are 9 terms. You add them all up, and you get just 2 terms. Okay? Everything combines into these 2 terms. Moreover, you can draw some crazy pictures. And that's not even the end of the story. There's even some crazier object called a polytope whose volume is the wave function. But okay, it's one crazy thing at a time. So this is the answer for the flat space wave function. But it's fun to just check the singularities. You just sit. So if you send k1, 2, 3, 4, 5 to 0, you manipulate this into seeing that you're going to get product of propagator for this times propagator for this, like in flat space. Or you can send this guy to 0 and see that you get products of 3-point wave functions and so on, shifted 3-point wave functions. So just check, it's fun. So at 3 level, actually that's it. Then you can prove that these are all the possible singularities. Every time that you send the sum of energies flowing into a diagram to 0, then the thing factorizes. And they're all poles, all simple poles. in flat space. In de Sitter space, unfortunately, the story becomes messier. The location of the singularities is identical, but the singularities can be of different nature. They can be higher order poles, they can even be cuts, they can be logs. Okay? Okay. Now let's go back to 4-point de Sitter bootstrap. So now we know where the singularities should be. Let's go back to our, so this was a toy model, everything massless. Everything is very nice, very simple. So now we go back to this de Sitter case where we have mass and spin 0. And here m squared equals 2h squared. And the strategy to, so you could have written, what is the difference? You could have written the bulk to boundary propagator is actually not very different for conformally coupled scalars, okay? It's just some plane waves. The problem is this guy here, because if you remember, the massive wave function in de Sitter space is a Hankel function. It's a mess. So there, instead of exponentials, you have products of Hankel functions. So you need to do nested integrals of products of Hankel functions, okay? And this object is a complicated object. So is there something else that we can do to get some handle on the answer? We can't do direct integration, but we can try. So the strategy would be, instead of direct integration, would be to look for how the symmetries act on them and impose the correct behavior at the right singularities. Okay, so the symmetries give a very broad requirement, so many things are compatible with the symmetries, but the singularities are very strict. Okay, if you have loops or if you have some other crazy stuff, it can be compatible with the symmetries, but it's not going to have the right singular structure. And the point about bootstrapping is that if you impose all the symmetries and all the singularities, the answers are more or less unique. So, before we embark on this mathematical endeavor, what should the answer look like? John Wheeler taught us that before solving a problem, you should know the answer, right? So, what should the answer look like? So you have a polygon, like a quadrilateral, right? And just like triangle are either isosceles or squeezed, then you should look into two possibilities: the square versus, let's say, I always get this, something that looks like a kite, okay? Something like this. So what's the behavior of this 4-point function, these two limits? So what do you expect when it's a square? Nothing? What do you expect the answer to look like when the momenta are all of the same magnitude, when they're in the form of a square? What should the answer look like? In terms of the physics of the answer, what should capture? Do you need to know everything, the full details of the massive propagator and so on in this limit? Remember, they have the same wavelength, so what happened to them during inflation? They were stretched by the same amount. So what kind of physics can give rise to this? It's just local. So it's just some contact interaction. So it should look like a contact interaction around this limit. On the other hand, what happens when you generate a big hierarchy? So here I'm in the S channel. I'm trying to make the S exchange momentum be very, very, very small. So what am I doing in this limit? I'm just measuring the 2-point function of the exchange particle, okay? So the signal is dominated by essentially the 2-point function of the exchange particle. So the 2-point function, sigma ks, sigma ks, but now it's evaluated at different times, eta 1, eta 2, because it's not the late time limits, okay? It's the bulk 2-point function of the field sigma of the, but at what time? What is the most dominant contribution? At what time? The blue particles, they act as a probe. They're just a probe that you're using to measure the 2-point function. But when is the probe the most efficient? When is the particle production of the blue guy the strongest? When it crosses the horizon. So K1, K2, K3, K4. So eta 1, K1 plus K2 should be order 1, K3 plus K4, eta 2 should be order 1. So this should be essentially the proportional to the 2-point function sigma ks evaluated at 1 over K1 plus over K2, sigma ks evaluated at 1 over K3 plus K4. Okay. And we'll see that. We're going to see the physics of the 2-point function of the messenger appearing in this limit. So, what's our strategy? First, we need to, before understanding the exchange diagram that is complicated, we should extend contact diagrams because they only have total energy singularity. So at least the singularity structure is as simple as possible. But now we have a novelty compared to flat space. So in flat space, the wave function of the universe is very simple, but we break time translation symmetry. So it's not a maximally symmetric type of situation. If we boost, we change the surface. Now, the late time surface in the Sitter space is special in that all the Sitter isometries act nicely here. So there's going to be some extra juice. So we lose at this level of simplicity of the types of correlators that appear, but we gain in that we have extra symmetry juice to squeeze. So there are 10 isometries that play nice with this correlator. So let's start with contact. So first part, contact interactions. Let's forget about exchange for a second. Okay. Actually, this one, for lambda phi to the 4, for conformally coupled scalar, what's the answer? This you know. Does it matter that we're in the Sitter space? It's conformally coupled, and it's lambda phi to the 4. It's a conformal interaction. So what's the answer? Exactly like in flat space. Okay. It doesn't know that we're in curved space. So this one we can do. Okay. Now if you put d phi to the 4, then the answer is complicated. But now I'll teach you a little trick. If you know this context diagram, you know almost every possible context diagram. But you'll see that there is subtlety now. So let's keep this in mind. Let's talk about the symmetries. So the 4-point wave function coefficient of a conformally coupled scalar. So conformally coupled scalar decays at late time as eta to the 1. And the wave function coefficient will have scaling behavior as if you were a CFT operator of dimension 3 minus 1, because a 3-dimensional CFT. So it's like a 0, 1, 0, 4, where the dimension of this operator is 3 minus 1, 2. Okay? So it has scaling weight 2. Just because you have to integrate over d3x, it needs to be dimensionless. So if this has scaling weight 1 at late times, this must have scaling weight 2. Translation implies delta function. That's not surprising. Delta 3 of k1 plus k4. Rotation implies that it only depends. So we had 12 pieces of data, right? The 3 momenta of the 4 particles. So now we are down to 9 pieces of data. There are 3 rotations, so you should get 6 rotational invariant quantities, and it's convenient to choose these ones: K1, K2, K3, K4, Ks, and Kt. Kt is just K1 plus K3, okay? Ks is K1 plus K2. Now, when we say that we are on the S channel, this is now dynamics, okay? So rotational symmetry tells us that it depends on all of these 6 variables. Then if we drop this dependence, it's a dynamical assumption that we're only looking at S channel diagrams. So S channel diagrams do not have T dependence unless the particle has spin, okay? Let's forget about that for now. Now we have 4 more isometries to exploit. So dilations. So the total scaling weight is fixed. This is a nice little exercise, but I'll just tell you the answer. So the total scaling weight, dilation weight, is minus 3 coming from the delta function. So the delta function carries scaling in k. So it goes like 1 over k cubed, plus the sum over all the dimensions. So each operator has some scaling dimension delta. Sorry, I don't like. Sorry. Maybe it's in momentum space, yeah. Delta minus 3. Because the minus 3 is because we do the Fourier transform. So we go to momentum space for all the particles, delta I minus 3. So now there are 4 of them. So, and they have each one scaling dimension 2. So I get 3 plus 4 times 2 minus 3. Just like the picture over there, 2 plus 2 goes like 5. So this should give, if I didn't make a mistake, minus 1. So this has scaling weight minus 1. Okay. So you can take whatever momentum you want, build dimensionless ratios, and soak up the scaling weight in one of the momenta. So you can write psi 4 as 1 over Ks times some function of the K1 over Ks, K2 over Ks, K3. These are dimensionless functions of the momenta. Now we have three more symmetries, special conformal transformations. And this I'll just tell you the answer because it takes some work to find the result. So you diagonalize, there are three of them. Two of them you diagonalize by making psi 4 be 1 over ks times a function. You just add these guys up, k1 plus k2. That's not surprising. Why? Remember that if you go here, it doesn't really depend on K1 and K2 separately because the propagator, the bulk to boundary propagator, is morely like flat space. It goes like e to the I k eta. But there is a propagator of 1, propagator of 2. So e to the I k1 eta, e to the I k2 eta. So it's really a function of k1 plus k2. Right? And okay, ks appears here. But the K1 and K2 always appear in this combination in the S channel. Okay? So that's why this is a reasonable thing to do, to combine them. And turns out that this diagonalizes 2 of the 3 de Sitter isometries. The last one imposes a differential equation in this function. So let me write down the answer. This you cannot do after stake. So this you need to go on Mathematica and do it. But I'll spare you the pain. So let me call this... Sorry, I messed up. What do you mean? There are 3 special conformal transformations. 2 of them are automatically satisfied if you write an ansatz like this. But there's one guy left that will impose a condition on this function. Sorry, let me call this 1 over u. Let me call this 1 over v, okay? So u is ks over k1 plus k2. V is ks over k3 plus k4. And now they satisfy an interesting partial differential equation, okay? So f, it's a function of u and v, must satisfy. This is the constraint of boosts. Just kinematics. I already put some dynamics because I dropped the KT dependence and I used this ansatz, so I am definitely not in complete generality. I am gearing up for a diagram of this type. I'm going to miss stuff that is spin dependent, for example. If the particle is spinning, this ansatz is not the right thing to do. But it solves a PDE. Where delta U is given by this formula. This is a hypergeometric operator. So any function that satisfies this differential equation is compatible with kinematics, the Sitter kinematics. Let's test. Notice that it has the right scaling weight, minus 1 over ks. And now we write k1 plus k2 divided by ks is 1 over u. k3 plus k4 over ks is 1 over v. Put things in the numerator. Now you can just, believe me, you can pull Mathematica and you can compute delta u acting on this function. It's going to give you the same as delta v acting on this function. Okay? So it satisfies the constraint. So that's good. So now I claim that we can find all S-channel context diagrams with zero work, just from kinematics. Just like in flat space, we say, oh, all context terms in the S-channel are powers of the Mandelstam. You know, constant times S, constant S squared, S cubed, S to the fourth. How do I build the analogs of higher powers of the Mandelstam here? What do you have? Remember that the requirement is it's compatible with the de Sitter symmetries, and it can only have a singularity when the total energy goes to zero. Here, total energy goes to zero is U plus V going to zero in these variables. So what do you have a guess of what they should do to build new solutions, bootstrap all the context interactions? Guess. It's physics. Oh, that's how the sausage gets done. So you need to guess. No. Like mindless. What is something that you can just do it and get something that solves the equation? There's no factorization because there's only one singularity. I need to produce a new solution of this constraint that is only singular as U plus V goes to zero. What do you suggest I do? Why do you think that multiply by 1 over U plus V, it's not gonna... What else? What else do you suggest? No. If I tell you, you're gonna be upset. Do you wanna try one more time or? Constant, no, because it doesn't have U plus V going to zero singularity. Is this a context term? This is a second order operator. It's going to produce only a singularity as U plus V goes to zero. And obviously satisfies this because delta U and delta V commutes and delta U commutes with itself. So it's a new solution. So how do you get another context term? Now that I showed you this. So you generated all the analogs of powers of Mandelstam. Okay, so if you do it once, you're gonna get U plus V cubed times some numerator, some interesting numerator that depends on U and V. You can check that as you send the total energy to zero, this numerator will conspire to become our old friend Mandelstam as flat, but upstairs. Okay? So now there's a novelty. So you see, in flat space, there was no scaling weight of the... So in order to generate the richness of powers of Mandelstam, because of scaling variance, you're forced to have higher order poles in the total. So you compensate for the numerator depending on more momenta by raising the power of E total. This, strictly speaking, does not generate all possible context terms because you can have analogs of in flat space like S times T times U. I'm just generating the analogs of powers of S. But now you have a strategy. You can just write k1 plus k2 plus k3 plus k4 to an arbitrary power. Let the numerator float, depends on these 5 variables here. At each order, there's only so many things you can write down because of scaling weight, and you fix the coefficients by imposing boost symmetry. You classify all possible contact interactions at 4 points in de Sitter space. Okay? I think it's pretty cool. No? So that's it. We bootstrapped all. So and you can reverse engineer. If you take delta U, it's related because it's S channel. It's a bit related to writing phi d mu phi squared d mu phi squared. Which of course, if the phi is not charged, you can integrate by parts and relate it back to phi to the 4th, which is the statement that if you sum over permutations, the cubic pole disappears and you go back to simple pole. But in the S channel, if you have a selection rule, if you charge the scalars, you can't get rid of this vertex, and it's the U plus V cubed contact. Then if you hit with another delta U, you get U plus V to the 5th, it's going to be d phi to the 4, and so on and so on and so on. Okay? So we're done. We bootstrapped all contact interactions. And now let's try to say something about let's try to say something about the exchange. Okay. So what's the difference? What's the novelty with the exchange? It can have singularities as k1 plus k2 plus ks goes to 0, and k3 plus k4 plus ks going to 0. Okay, this is the novelty. Now let's look at the differential operator. Delta U well, if you want to look at the singularity of a solution of a differential equation, you should check the zeros of the thing that multiplies the highest derivative, right? So this is singular at 3 different places. U equals 0, U equals 1, plus 1, U equals to minus 1. So U equals 0 is Ks going to 0, which is the soft limit. Well, not soft limit external, like more like the collapse limit when you make this very soft. It's the limit in which you would see particle production. So this better be an output, okay? We don't know how to normalize this singularity. We don't quite know what to do there. So this is going to be an output of the analysis. We're going to see particle production there. Now U equals plus 1 is Ks equals to K1 plus K2. So this doesn't look good. It's just the collinear limit, okay? K1, K2, K3, and K4. In this limit, nothing should happen. But strictly speaking, the differential equation tells you that there are singular solutions there. And you people grilled me about this alpha vacua, okay? So alpha vacua have a life here. So if you allow for alpha vacua, so we will forbid. Forbid. It's related to choice of vacuum. If you allow for alpha vacua, or some excited state at the beginning of the universe, then you will get things in the that look like this appearing in the answer. Okay, this makes striking prediction that you look in the sky and if you align the momenta, boom, the signal is enormous and we don't see anything. So either use mirror this. You say, oh, you know, I break symmetry and I add something, some scale that mirrors this, or you just rule out this possibility, okay? I'm going to rule out it's related to choice of vacuum. You see that if you do vacuum wave function, these types of singularities never appear, but they are hardwired in the kinematic constraints. So we're going to use it as a boundary condition. We're going to get some differential equation, and we're going to use the absence of a singularity in this limit as a boundary condition to solve the equation. Finally, this is our friend, Ks. Factorization. Here we know it has to become singular, and we know how singular it has to be. It must be related to the 3-point function. Okay? It's the limit in which I take this guy here, drag it to the past. It should become 3-point scattering amplitude, which again for scalars is always a constant, even they're massive, times this 3-point function of 2 conformally coupled scalars with one massive particle, which I did not discuss, but we can discuss. But maybe I'll sweep it under the rug for now. So delta U and delta V have the partial energy singularities. Delta U has the partial energy singularity in Ks plus K1 plus K2, and delta V has the partial energy singularity in K3 plus K4 plus Ks. We're missing the total energy singularity. So, but remember, delta U is not some crazy operator that came out of nowhere. It's boosting. It's moving the points around. Delta U minus delta V tells me that if I boost both points together, nothing happens. But delta U only boosts this guy because it only cares about the momenta that flow into this vertex. So can I use this for something? If I only shake this guy around and keep this one fixed, does anything come to mind? Is there anything I can do to try to find something, make progress? So I'm telling you, with delta U, if I apply delta U, I'm capable of moving only this vertex around without touching this one. If you could do that, what do you suggest doing? Move it where? Yeah. Move it here. Yeah, no. Move it here. Move it here. If you move it here, you collapse this into a context term. And we know what the answer is. And by the way, this has the singularity we were missing. And now we're done. Now we have some object that has all the singularities. So we apply delta U and play a bit with the function, and we should be able to collapse the internal propagator and get a contact interaction that has the singularity. Okay? So if I add delta U, F it should be, and of course, I must have similar equation in delta V. Am I allowed to add anything else? Remember that the ultimate kinematic constraint is delta U minus delta V F equals U. This is just kinematics. Now this is some dynamical assumption that we're trying to just collapse the internal propagator of the exchange to get this guy here. So this only knows about kinematics. So there must be a little bit left of dynamics related to the mass of the particle, right? Because it depends on the mass of the particle that we're exchanging. So what freedom do I still have in this equation to be compatible with the symmetry? What can I add in such a way that if I subtract both equations, I get delta U minus delta V equals 0? Constant. Okay? I can add a constant. This constant is related to the mass of the particle. So let me be explicit. Is the mass of the particle in Hubble units minus 2. Our old friend from the first lecture. Minus 2. Now we traded nested time integrals of Hankel functions for a pair of ODEs that we can beat to death with 19th century mathematics. Okay? When we say, we have a Bessel function, this is as good as it gets. What is a Bessel function? It's not a J, right? It's the solution of a differential equation with certain boundary conditions. So this, now we understand this 4-point function at the same level that we understand a Bessel function. Solution of a pair of ordinary differential equations with boundary conditions. Yeah. Maybe if you were symmetric in U and V, but there is one extra constraint that would tell you that this is the right thing to do, which is if you send the mass to infinity, then you should be able to integrate out. There's no motion to do, it's just contact. So if you send mass to infinity, you erase this, and the answer is just a contact diagram. So if you added some function of U and V, you would not get the contact solution. Right? So that's the... Well, there's a more mundane reason because this is the right answer, but I was trying to argue just based on symmetries, but there's a more straightforward way of getting this answer. But it's boring, so I wanted to argue that this is the right way. You were questioning if I could add here some G of U and V, right? Is that what you had in mind? Right. So it needs to depend on the mass, and it needs to be such that when the mass goes to infinity, you get back the contact interaction. So that's the simplest thing to do. Maybe if you add the G of U and V plus M squared, maybe this is possible. Yeah. By the way, if what does this look like to you? Maybe it's too telegraphic. Okay. How do we derive this from a more straightforward way? So if you write the wave function psi4 in terms of integral d eta 1, d eta 2, k of k1, eta 1, k of k2, eta 1, g of ks, eta 1. So these are the bulk to boundary propagators for particles 1 and 2, the bulk to bulk propagator and bulk to boundary propagators, right? Is there any equation that this guy satisfies that you imagine could turn this into a contact interaction? The contact interaction is just the product of 4 bulk to boundary propagators at the same time, right? But the Green's function solves what equation? What's the equation that the Green's function satisfy? It's a scalar field. What is the equation that a scalar field satisfies? Klein-Gordon equation. So this solves the Klein-Gordon equation. Box plus m squared is delta function. Eta 1 minus eta 2. So if you can engineer, but you don't have access, so you can't manipulate time derivatives. The box has time derivatives. But if you can manipulate from the outside, integrating by parts and so on, acting with momentum derivatives, and you can somehow generate time derivatives acting here, delta U messes around with these guys, manipulates them in such a way that it produces eta 1 time derivatives. So you produce box with respect to eta 1, and then you collapse the propagator into a delta function. So this is the boundary version. It's the boundary version of acting on the left, collapsing the propagator to the right, and getting a context term. Okay? Remember that delta U is analogous to Mandelstam. So S flat plus m squared F. Context term, this is 1 over E total, is just lambda phi to the 4, is lambda. So an exchange solution is lambda divided by S flat plus m squared, which is the right answer, right, for exchange diagram. So this equation here is just the analog of taking the usual exchange solution with a pole and putting this on the left-hand side. Okay? So that's it. It's just that now there's a pair of them because you can't boost to the center of mass frame. It engineers the Klein-Gordon operator from the left or from the right. So we have a boundary differential equation. That's beautiful. We bootstrapped our 4-point function. You can just solve it. It's a second order equation, so we need 2 boundary conditions in U, 2 boundary conditions in V, but we have them. You go to U go into 1, there should be a singularity, you forbid it. There will be a logarithmic singularity in this case. You just ensure that the coefficient in front of the singularity is 0. That's one boundary condition. Second boundary condition is that as U goes to -1, there will be log of U plus 1 appearing. And you want to relate it to the 3-point function, okay? To the 3-point function of 2 conformally coupled scalars talking to a massive scalar. Okay, so we would need to learn how to compute psi 3. Psi 3, where you take 2 conformally coupled scalars and 1 massive scalar of mass m. In principle, I'd have to teach you how to do this, but now there is something very beautiful that happens. Remember that delta U was Ks divided by K1 plus K2. In particular, it's like 3-point data, okay? 3-point data. If you now, and it forms a little triangle. 1, 1, 2, Ks, 3, 4. It forms a little triangle. It conserves momentum on its own. You can forget about the right. Okay? So now these are 3 momenta. They're conserved 3 momentum, and they have their associated energies. So what is the 3-point function associated to this? Now I just tell you the answer. Okay? So psi 3 is going to be Ks to a certain power. So now it's not 1 over Ks here because the scaling weight, remember, depends on delta I minus 3. So this guy, because it's massive, is going to have a different scaling weight. It can redshift away and so on. So there's a little bit of a difference here. But then there is a function that depends on the dimensionless ratio. And by the same story, these are conformally coupled. Only K1 plus K2 appears. K1 plus K2. F of U. So it solves, so this function, let me call it f3, the 3-point function. This function here of this variable u solves this equation here with a 0 on the right-hand side. It's a homogeneous solution. Okay? So just boost symmetry gives you this. That's pretty cool, because then the homogeneous solutions allow you to adjust the normalization of the second singularity. So the second singularity, the second boundary condition, is related to factorization, and the homogeneous solutions of this equation will give you a way to normalize the proper factorization. And you're done. You're done. You know everything you can possibly know about this function. So we stop with 15 minutes. Is that right? So I want to finish on a high note. Solving the equation, as you can imagine, a pair of ordinary differential equations in two variables, not exactly bedtime reading, but it's a little bit tedious. But I want to go to a little limit in which something very beautiful happens. I'm not going to solve it in full generality. That would be torture. So let's try to solve the equation. As u goes to 0, I'm not even going to solve the equation. As u goes to 0 and as v goes to 0, I just want to make a point. U over v psi fixed. I'm keeping the ratio fixed. And I rescale f. So f equals v f hat of psi. So, well, the delta u and the delta v equation become the same, and the equation becomes something like this: psi squared d squared. I mean, you're sending everything to 0, so you zoom only on one of the singularities. You forget about the other ones. But I just want to show you the particle production, and it's going to be rather spectacular how it appears. All right, yes. Now let me, remember, psi is just some ratio of momenta, okay? Just some ratio of momenta. But now let me do, let me change variables, call this e to the t, f hat psi to the 1/2 f tilde. What do you think will happen? Let me write m. It's just a change of variables to make the. Let me write it as mu squared plus a quarter. Just introducing some proxy for the mass in Hubble units, okay? This is what the equation is. What is this? Harmonic oscillator. You just see a harmonic oscillator with some forcing term. So the ratios of momenta are your probes to measure the time evolution of this probe particle as it traverses the geometry. And the particle is just a free particle, it's just a harmonic oscillator that is tracing the geometry, and is getting kicked by the expansion of the universe. That's it. Okay? So you're seeing time evolution without having access to the timeline of the universe. Just by dialing. As you dial up and down the ratios of momenta, you see the particle traveling through space-time and picking up a phase because it's oscillating. So you get a kick, which is related to this. We only see the tail, the kick that is related to the equilateral when things are in the square configuration. You don't really see it in these limits where u and v going to 0, but you see a little bit of it, and then the signal oscillates, and the oscillation you're just seeing the e to the I e delta t as the particle picks up a phase as it traverses through the universe. So you should be able to look up in the sky and see a 4-point function that modulates up and down, and you're reading off a quantum field traversing through inflation at the beginning of the universe. So that's pretty sweet. You can even see particle production here through something a bit like what people call resurgence. Let me maybe illustrate this point and then we stop. It's related to, there was a question about integrating things out. You see that you can never integrate things out fully in inflation. By the way, let's go back to the original equation, delta u plus m squared over h squared. Let me drop the 2. Let me make the mass very big, okay? uv over u plus v. So, naive solution. Your first year undergrad, solve this equation, no big deal. You just do this. And then you learn, no, but this is a derivative. You need to take derivatives. I'm like, no, but I know Taylor series. So I just do this, 1 over m squared over h squared. Then uv over u plus v minus delta u over m squared over h squared, uv over u plus v, plus. Actually, this is a pretty reasonable thing to do if you think about it. What is this? This is just the contact term from phi to the 4. This we just learned like 20 minutes ago. It's related to the irrelevant operators, right? So it's the analog of saying that g squared over s flat minus m squared is like g squared over minus m squared, 1 minus s flat over m squared plus, right? This is a completely acceptable expansion of the answer as long as s flat is much less than m squared. But here, what does it mean for delta u to be smaller than mass scale? Some operator being small. And you can actually, this is an expansion in nothing, okay? You can make this very big, but there is always if you work at fixed kinematics, if you go, it goes down, 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 down. At some point, you see that starts to pick up again. So there's never a sense in which you are doing you do observation fixed kinematics. You never fully integrate out a certain massive field. But this is what one would call the EFT expansion, meaning you parameterize the answer by contact self-interactions. But let me show you that there is no analyticity. In particular, notice that it's analytic in the mass, right? Or in Hubble. It goes like Hubble squared over m squared, Hubble to the 4th over m to the 4th. And particle production, remember, is Boltzmann suppressed. It's e to the minus m over h. which is non-analytic. It's like an instanton effect, if you wish. It's you'll never see in perturbation theory in H over M. So let me just quickly show to you how you see that in this example. Just a little bit. And tomorrow I'll get back to it. Just to make you happy before you go home. It's a beautiful piece of physics. So you go about your day and you want to solve this differential equation. Use Frobenius method. Just power law solution. Plug it on the left, plug it on the right, match coefficients. Great. So you can solve for small x, for small psi, sorry. You can find a particular solution. Looks like this. F tilde small psi minus 1 to the n, psi to the n plus 1/2 divided by n plus 1/2 squared plus mu squared. Okay? It has finite radius of convergence. I mean, you can resum this, by the way. It's a hypergeometric function, but you don't know anything about hypergeometric functions. Okay? So you don't resum. You're like, oh, okay, this is only valid for psi less than 1. Now let me go and then solve for large psi. Let me expand around psi equals infinity. Then I find another solution. It looks like this. So now I need to find a particular solution everywhere. So I have a particular solution for small psi, a particular solution for large psi. To make sure that it's the same function, I need to match, right? So xi equals 1 at the circle xi equals 1. I need to make sure that the function and its derivative are continuous because it's a second order equation. So, but it's a particular solution. So f tilde plus minus f tilde minus, at least on the, it's a homogeneous. So you're free to add some homogeneous related to the zero modes of the operator. You're free to add some homogeneous solution to, let's say you keep this one untouched and you add some homogeneous solution here to make sure that the function and its derivatives match. Okay, what are the homogeneous solutions of this equation in terms of mu? The homogeneous solutions, there are two of them, psi plus or minus I mu. Okay? Notice that there's already something amusing, that the mu dependence, instead of appearing downstairs here, is appearing here. And then when you match, you find that the homogeneous solution of the equation. You wanna, I'm just trying to find a particular solution everywhere. Okay? So I'm always free to add zero modes. It's not related to, it's a bit like boundary condition, but I'm not trying to find a function. I'm just trying to find one particular solution that is valid for all values of psi. And then if I want to claim that the function f tilde is defined to be f tilde less for psi less than 1, f tilde greater for psi bigger than 1, they have to match at xi equals 1. Okay? So I'm allowed to add a plus so that then this is a function that has continuous derivative and a continuous value. And lo and behold, and then I stop, a plus, it's a simple exercise. You can do the resummation, 1 over 2 I mu, 1 over cosh pi which a large mu goes like e to the minus pi mu, which is particle production for large mu. Okay? So you see that just in trying to find a particular solution that is well defined everywhere, you see that this particle production piece is exponentially small in the mass. All the terms are mu suppressed, and this is exponentially small piece in the mass that you need to add there just to have a solution that is well defined in all kinematics. Okay? So now with this, you have a particular solution everywhere, and then you're still allowed to add homogeneous terms, but then you add homogeneous terms upstairs and downstairs to fit boundary conditions, okay? This was just to find a particular solution that is well defined at all values of psi, after which you're free to fix boundary conditions by adding homogeneous terms, both rows. I'm done. See you tomorrow.